Hi everybody. So this next section 5.5 is on the substitution method and indefinite integrals involved in this. We'll talk more about the indefinite integrals in the next section, which is kind of unusual. Typically most books will include these together in the same section, but in any event. So this is sort of the first method of integration. So like I said, one thing you will do is if you go on and take Calc 2 is you will study several other methods of integration. So the way the substitution method works is you basically try to replace something in the integral with something so that if you take its derivative, you get sort of something that's like what's in the rest of the integral. At least that's the way it's supposed to work. So you'll basically make some substitution for g of x in the integral, and then by computing that, you'll basically replace all occurrences of the variable x with the new variable u. So it's sort of a transformation of variables, where you're transforming the integral from a variable with x into something with the variable u. And the idea is hopefully this new integral that you get will be easier to integrate than the original integral, and then you just have to substitute back, right? Because you want the answer in terms of x when you're done. So here's a simple example. So again, you look at something like this, you might think, well, man, that looks really complicated. And you should just try just regular integration at first, because it may be you might be able to just think of this backwards and see what the antiderivative is. But if you don't, look for something in the integral so that if you take its derivative, you get what's left over. So if you think about like e to the x squared, if you look at the derivative of x squared, that gives you 2x. So the substitution we want to make is probably u is equal to x squared. Now sometimes when I do this, I don't always see what it is, or you don't necessarily see what it is right away, but at least try something, right? Trying something might give you sort of an idea of what to do. So the idea then is I will replace this with u, and then if I take the derivative here, because you not only have to replace the x up here, but you have to replace the dx as well. If I take the derivative of that, I'll get 2x, so that implies that du then, if I multiply both sides by dx, is x squared times dx, right? So that means that this thing here, you can replace that with du. So this will become e to the u, and I can rearrange, if you really want to rearrange this, you can, right? Because you're basically just multiplying. If it makes you feel more comfortable moving those two things next to another, you can do that. That'll give you du, and so you'll get e to the u du, and then take the antiderivative of this with respect to u. So think of this as the antiderivative of e to the x, except you're using u instead of an x. So in that case, if you take the antiderivative, you'll just get e to the u, right? And then because this is an indefinite integral, right, because you don't have limits of integration on your integral, right, you should get some constant there. And then don't forget to substitute back in, right? Don't forget to replace the u with x squared when you're done. Here's another example. So you got something like this. Again, it is kind of hard to tell what to do for the substitution. So if you're not sure, at least try something. But look for something in here. When you take its derivative, you kind of get what you want. So if you look at this, if I take the derivative of this, right, I'll get 3x squared. Now it's not exactly x squared, but it's only off by a constant. Remember, constants we can factor outside of the integral. So I think the substitution for this one that you want to make is x cubed plus 5. And if you take that derivative of that, right, you'll get that, and then multiply both sides by dx, right? So that means the x squared dx, you can replace that. If I just divide both sides by 3, I can replace the x squared dx with du over 3. So I'll replace that with du over 3, and then the x cubed plus 5, I'll just replace that with u, right? And again, ultimately what you want is you want this integral to be easier than the one you evaluated, that you started with, right? If it's not, you've probably done something wrong, right? So this is a lot easier to integrate, right? U to the 81, you just raise the power by 1 and divide this by the same thing. I'm just using the power rule here, right? The fact that the antiderivative of x to the n, right, is x to the n plus 1 over n plus 1. except I've got u instead of x. And then that 1/3 though is still out in front, so you got to multiply that, and then don't forget your constant there on the end. And then also don't forget to substitute back in for your u when you're done. Here's another example, right? So for this one, again, it's kind of hard to tell, but we're just going to do u is equal to x squared, right? Because the antiderivative, or the derivative of that is just x. So taking the derivative of that, right, we'll get the derivative of u with respect to x is 2x. So replace the dx over, the x dx with du over 2. Replace the x squared with u. Antiderivative of sine is negative cosine. Again, just don't forget to replace that when you're done, and then also don't forget your constant. Here's something, again, that, it's kind of hard to tell what to do here. But let's try u is equal to sine x plus 1, right? Because the antiderivative of, or the derivative of that is cosine x, right? Well, it's got a 2 in front, but pretty much the same thing. So replacing that with u, and this with du over 2, right? The antiderivative of u squared is just u cubed over 3. Don't forget your constant, and then don't forget to put that back in for x when you're done, right? Don't forget those two things. Here's another example, right? Let u be 1 plus x to the 4th. Take the derivative of that, right? So replace 1 plus x to the 4th with u. Then you get that when you integrate, and then again, don't forget to put that in, and don't forget your constant. Now this one is a little bit different. Like I said, when you take the derivative, you want to see what you have left in there. Now that isn't always the case, but most of the time that'll work. Here's an example where you can use a little bit of a trick. So in this particular case, right, if you look at x or 1 minus x, you don't see its derivative in there, right? Because the derivative of this is going to be 1, derivative of that's going to be 1. Neither derivative is going to have an x in there. So like I said, try something, right? So let's try u is equal to 1 minus x. So we'll come back to this part later. So the derivative of that is just negative 1. So that means du is the same thing as negative dx. So that'll put a negative sign in front of our integral. And then you can replace this with u. Now the only trouble with that, though, is we've still got this x out front. So how do you get rid of that? Well, you can take this equation up here and solve that for x. You can replace x with negative u plus 1, right? So this becomes u, and that becomes that. And you might say, okay, well, great, I still can't integrate that. But remember, this is just the same thing as u to the 1/2. So take that and multiply it times each one of those, right? That'll give you u to the negative 3/2 plus u to the 1/2. And then here I'm just going to take the negative and pull it out, I don't know, just to make things easier. So if I do that, that'll become positive, that'll become negative, and then just use the power rule, right? Just add 1 here and here. Same thing with that. Again, don't forget your constant. And then also when you're done, don't forget to replace all the occurrences of u with x, right? And then that will be your answer. So the substitution rule is a little bit trickier than what I'm letting on here, but that's one of the first things you want to try. If it's not something obvious, like the integrals we've tried before, the first thing you want to try is some substitution method, and you'll see later on in Calc 2 when you do methods of integration, right, you basically just have to, you'll be given several different tools and you have to decide which one to use. Try simple stuff first. Now there are a couple other things that can happen with regard to this technique. One is that you might have to perform some sort of algebraic manipulation or use some sort of trigonometric identity, right? So for something like this, and like I said, a lot of these integrals you can look up in the back of your book, but I may expect you to do these explicitly by showing the substitution method, because that's how a lot of the integrals in the back of the book or online were obtained, is some method like this. So again, it's not the method that's important, right, in case you need to reconstruct these all on your own. In this particular case, you've got sine squared x, right? If you use the trig substitution for that, just break this up, right? And then here, when you're integrating this, right, you technically need to use substitution, right? Because the antiderivative of cosine x is not just sine 2x, right? You have to divide by a factor of 2. So a lot of times when we do more advanced stuff, I'm not going to explicitly do the substitution because it's just so easy you don't need to do it. But when you're dealing with this here, right, you really should do u is equal to 2x. And so the derivative of u with respect to x will be equal to 2. And so du will equal 2 dx, right? And so if I do that substitution, I'm going to replace dx with du over 2. Right? So you might wonder, well, where is that extra 2 coming from? I mean, this first 2 comes from the fact that you're dividing by a half, but the second 2 comes from the substitution method, right? And you know, if you look that up in 4.8, right, we kind of had that, right? We said that like the antiderivative of cosine of kx, right, the antiderivative of that was 1 over k cosine kx, right? So kind of already talked about that. You might have wondered, well, where was that extra k coming from? Well, one is the fact that when you just take the derivative, you got to use the chain rule, so you need that k to cancel out the k, but you can also think of it as coming from the substitution rule, and then don't forget your constant there, right? Here's another example. All right, so when I take the antiderivative of this extra 2 comes from the substitution, but that substitution is so simple, a lot of times I won't work that out from now on, so just be aware of that. Here's some more examples that might involve some sort of algebraic manipulation, right? So there's really no obvious substitution to make here. So what I'm doing here is I'm multiplying on the, remember this is really the same thing as 1 over e to the x. So I'm just doing some sort of algebraic manipulation here by multiplying on the top and the bottom by e to the x. And I can do that because it's still a fraction. Now doing that allows me to make a substitution here, right? I'm letting u be equal to e to the x, right? Because I can write this as e to the x squared if I want to, right? Because raising a power to a power, you multiply the exponents. And then if I do that substitution, I get this, and then the antiderivative of this is just tangent inverse of u. Don't forget your constant, and then don't forget to substitute back in when you're done, right? Here's another example. This one's kind of tricky. What's the antiderivative of secant x? Again, I think we've maybe seen that in some tables already. But how did the first person get that? Because it's not obvious what you would do. There's not a whole lot to substitute here, right? I mean, you let u be equal to secant x, and then, well, the derivative of that is nowhere to be found in the integral anywhere, right? So in this case, and there might be other ways of doing this too, but one thing you can do is multiply on the top and the bottom by that, which would give you this, and then you let u be equal to the denominator, because it turns out that if you take the derivative of the denominator, you get the top, right? So you can make that substitution and then just replace your all the u's with x when you're done, right? So this is a little bit trickier than I've let on, but that's sort of the idea. Now there might be some problems here where you might run into some initial value problems, and so these are similar to what we did in the previous section. The only difference is you might have to use techniques of integration to solve them, right? So the idea then is to take this initial value problem or this differential equation and solve it, right? Figure out what function could you put in for y so that you'll get this giving these initial conditions. So just go ahead and integrate both sides. Now when you integrate this, you're going to have to do some sort of substitution. Here I didn't explicitly write the substitution down, but you'd want to let u be equal to x squared plus 8. And that will give you that, right? Because you'll get du dx is equal to 2x. So that's where that 2 is coming from, is from that. Pull the 4 out front. Use the power rule on that. Just add 1. And then don't forget to substitute back in when you're done. And then because we have an initial value problem, right, don't forget we can figure out the constant. So here's my function. So I'll just make, when x is equal to 0, y will be 0. So put 0 in for x and y. Solve that for c. You'll get c is equal to 12. And then don't forget to incorporate that into your final answer. And remember, you can always check this if you want by plugging into the differential equation, right? Take the derivative of this with respect to y and see if you get that. Right? All right, well, that wraps up 5-6. So the next thing we're going to look at is further substitution where we have definite limits of integration, and there's a couple different ways you can do that, right? Remember, these were all indefinite integrals. We didn't have any limits there. And we'll also look at calculating areas between two curves, which generally isn't too bad, but there are a couple of things you got to worry about there.